Okay. Well, hi everybody. So it's lecture 20, and I guess you can get the YouTube link from the upper left corner if you want to scroll back. Um, okay. So yeah, it's lecture 20. And since there was okay, so the midterm is on Thursday. It's released at 8 a.m. And sorry, there were some confusing messages regarding what's on the midterm. It covers material up to lecture 18. So in particular, random variables are not going to be on the midterm. So what's the plan for today? So I'm going to talk more about probability theory and then do a brief review of everything we've done since the last midterm. So first, I'm going to say a little bit more about linearity of expectation. As well as the relationship between random variables and events. Or actually, I'll do that in the second part. Sorry. So in the second part, I'll talk about the relationship between random variables and events, and in particular, the notion of the distribution of a random variable. And then finally, I'll talk about algebra with random variables. And independence of random variables. So actually, I won't be covering variance, at least explicitly today. We'll do that after the midterm. And then finally, at the end, I'll do a quick review. So, okay. So let me just recall the basic notions from last time that we're going to use this time. So last time, we introduced this very important notion of a random variable. If you have a probability space, S with some probability function P, then a random variable is a function from the sample space to the real numbers. And the main associated concept is the expectation of a random variable. Which we defined in one way, and we saw it had two equivalent formulations. One was as a sum over outcomes in the domain of the function. And the other was as a sum over values in the range of the function of the random variable. And maybe I should have drawn this last time, but there are actually some very kind of concrete pictures associated with these two formulas. So let me just draw them. So the first formula is a sum over the domain. And the picture associated with this is that if I were to draw a cartoon graph of this, then the domain here is the sample space S, or I guess this is the variable for the outcome S. And the y-axis is x of s. And so suppose you have some function on the domain that looks like this or something like that. So I'm going to draw two copies because I want to show you the two different summation formulas. Then the intuitive meaning of the expectation is it's just the average. It's just the average value of the function, right? So in this picture, okay, this is a cartoon. There are two ways of computing the average. So one way is I go over the points in the domain and let's say the function is height, and I just look at the height and then I compute the averages of all these numbers. But there's actually another way to calculate the average. So the average is just the area under this curve divided by the length on the x-axis. I mean, this is a cartoon picture, but that is what it is. The other way is to do the sum over the codomain or over the range. What I can do instead is I can ask, well, for any particular value in the range, like this is my R, what fraction of the domain has that value? And then I can repeat this for all the different values in the range. And you can see that if I do this, so here I'm summing, in the first picture, I'm summing over S's on the horizontal axis. The second one, I'm summing over R's on the vertical axis. But you can see that these are two different ways of calculating the area under this curve, which when you divide by the x width of this graph, you'll get the average. So that's what these two pictures correspond to for expectation. So any comments or questions on that? Okay. And the main property I wanted to emphasize.
I have a question about this.
Mm-hmm.
So where exactly in these two equations is dividing widths?
Yeah, the dividing is happening implicitly because these add up to 1. The probabilities add up to 1. So it's not happening explicitly, but if these were uniform probabilities, right? The probability of every point would be 1 over the size of the sample space.
Okay, so you're saying that
like
they are normalized and that's when the division happens.
Yeah.
Okay.
So this is so I mean, this is just a cartoon. So I should put this whole thing in quotes, but I'm trying to relate it to what you learned in calculus about area under the curve. That's a sum. That's not an average. To make it an average, you'd have to divide by, whatever you're normalizing by. And in that case, that's the size of the sample space. Does that make sense?
I have another question about this. Remember
Sure.
in the last lecture, there was mapping heads to the number of heads that we're flipping to. Like one head maps to 1, 2 heads map to 2.
Yeah.
In that case, the result is 1.7 something. So that's not less than 1. Or that's because we're summing things together.
Well, it doesn't have to be less than, right. So, I mean, the average value of x doesn't have to be less than 1. So an expectation is not a probability. It can be way bigger than 1. The thing that have to add to 1 are these probabilities.
Okay.
I'm not saying that this whole sum has to add up to something less than 1. That's not true.
Okay.
Yeah. I mean, here, since this is, I guess, maybe this is not help. I mean, this is really a cartoon. The real picture you should think about here is that there's a sample space and you have a random variable mapping the sample space to the real line. And the sample space actually partitions, sorry, this random variable partitions the sample space into subsets. Like x equals 1, or, like, okay, let's say, for example, the range of this random variable is like, as in the example in the last lecture, 0, 1, and 2, and okay, 3 in this case. Then really this is, you can partition the sample space into subsets depending on the value of the random variable, right? And so, these probabilities that appear in the second sum are the probabilities of these events, these subsets. So, I mean, this cartoon, the second picture is really the more accurate one. The first one is just to maybe relate it to what you learned in calculus. It can be made rigorous, but we won't be doing it here.
Makes sense.
Okay. And okay, I mean, I guess while I'm at it, I might as well say something about events associated. I was going to do this in section 2, but let me just do it now. Let me just say that an event so let me just call this a remark. An event is a subset of the sample space, okay? On the other hand, a random variable is not, it's a different type of object. It's a function. Okay, these are inherently different types of objects, but there is a relation between these in the following sense. So every event defines a random variable. So to correspond to every event, there's an indicator random variable. Call it 1 sub e, which is a function from S to R defined by the indicator random variable of an outcome is just 1 if that outcome is in the set E or 0 otherwise. And when you define this indicator random variable, then you know what's the expectation of this indicator random variable in terms of the event E. Anybody see that?
It works out to be like P of E, right?
Yeah, so it's just 0 times the probability of E complement plus 1 times the probability of E, which is just the probability of E. So you can turn events into random variables by doing this indicator construction. Okay, so this is the relationship between an event and its indicator random variable. On the other hand, every random variable defines a bunch of events. I've actually drawn them in this picture. For every value of the range in the range of X, there's an event, right? So this defines events. Let's call them E sub R is the set of S in the sample space, or yeah, such that X of S equals R. And you know, I mean, these are the events that appear in the definition of the expectation. I mean, let me just, you know, this is just the event X equals R. So you can go back and forth between random variables and events, but they're not the same thing. So defines events corresponding to numbers R in the range of X, or let me say corresponding to the range. And you know, you can define more complicated events, right? You can also define, I don't know, you can also define events like, you know, that don't just ask, is the random variable equal to something? You could define an event that is asking anything at all about the random variable, like, is the random variable, I don't know, less than 10? That's a valid event. So you can go between these two notions, but they're not the same thing. So any questions or comments on this?
So then, hypothetically, could you define multiple different random variables for the same event?
Can you repeat the question?
Could you define multiple random variables for the same event to solve different types of problems?
What do you mean for the same event? Do you mean indicator random variables or?
I mean, like, if you were trying to find the expected value of like rolling a six-sided dice, like one random variable would be what the number is on the dice.
Yeah.
But another random variable could be whether it's even or odd. So like you can define multiple different.
Absolutely. Yeah. So the whole art of probability is, okay, generally the goal is to calculate probabilities of events or expectations of random variables. And often it's not obvious how to do that. The whole art is to how to break it down into simpler events and random variables. So absolutely. And okay, does that answer your question?
Yeah, thank you.
And again, the key property of expectation was linearity of expectation, which was that the expectation of a sum of random variables is the sum of the expectations. So this really is, again, related to your question. You can use this to break down complicated random variables into simple ones. Let me show you two more examples. Since last time we did one example, but with derangements, right? What's the expected number of fixed points? Not derangements, with random permutations. What's the expected number of fixed points of a random permutation? We calculated that it was 1. So here, let me do another example. So suppose I throw n balls into n bins. I throw n independent balls into n bins. So that means for each ball, the probability that ball I lands in bin j is 1 over n. So equally likely. How many bins are going to be empty? How many bins remain empty on average? Okay, so is the question clear? Let's say I throw 10 balls in 10 bins. So what's the average number of empty bins? So before we solve this, anybody have any guesses? I mean, if you've done the calculation before, don't just say the answer, but anybody have any guesses for how many should be empty?
Zero.
0? Okay. So you're thinking if I throw n balls randomly into n bins, then most of the time I'm going to get exactly 1 in each bin? Is that what happens?
Doesn't sound right from a reality point of view.
Yeah, so then it's probably not right if it's not right from the reality point of view is important, I guess. So do you think there are going to be a lot of them or just a few? Do you think most of the bins are going to be empty or they're going to have a ball in them? Like the two extremes are all the bins are full, and the other extreme is I end up throwing all the balls into one bin. That also seems pretty unlikely, right? Okay, let's just go ahead and solve this. Unless anybody has any more comments on it.
There was like a cool idea in the chat that maybe it's something around n over e. I don't know.
Okay, yeah, that is actually the correct answer. It's n over e, but let's see why. Okay, let's see why. So, okay. So how do we solve this? Well, so this is the experiment. And we could write down the probability space, right? It's all possible. For each ball, I just have to choose which bin it went into. So it's all tuples of numbers between 1 and n, but I'm not going to do that. We're just going to work implicitly with random variables. Now what I'm going to do is I'm going to define a bunch of indicator random variables. So define x sub I to be the indicator to be 1 if bin I is empty and 0 otherwise. for I going from 1 to n. So I have n random variables. Okay. Now the total number of empty bins is the sum. Let's call this, this is now another random variable, x is the sum, right? Now, the nice thing is it's relatively easy to find the probability that one bin is empty. Okay. So what's the expectation of one of these random variables? Well, by what we said earlier here, that the expectation of an indicator is the probability of the event, this is just the probability that bin I is empty. Now, the beauty of this is this is now something that is just about one bin, right? Somewhere in here, we're now looking at bin number I, and we only care what happens here now. We just forget about everything else in this calculation. Now I'm throwing n balls. So each time I throw a ball, okay, now we have to solve this problem.
Question, Professor?
Yes.
Could you define it the other way around? Could you say that it's 1 otherwise and 0 if bin I is empty, or does it have to be in the specific orientation?
Well, usually you write otherwise after you've already written something above it, right?
Okay.
So you should usually write otherwise at the end. Okay. Well, let's use the rules of probability. So bin I is empty. So what does it mean if bin I is empty? Now, so there are like n balls being thrown into the bin here, right? And for bin I to be empty, ball 1 better not go in that bin, right? So what's the probability that, so what I'm going to do is I'm going to write this as an intersection of events. Is the probability that ball 1 doesn't fall in bin I, and the second ball 2, doesn't fall in bin I, and none of the balls do, right? So if you do this, you get n intersection of n events. Any questions about this step? Okay, now these are now even smaller events, right? Notice what I'm doing. I'm really zooming in on this process. Each of these events is an event involving 1 ball and 1 bin. Now, this is an intersection of n events. Do you see any nice structure of these events that would allow me to break down this probability further?
They're independent events.
They're independent events, right? So whatever happens with ball I has nothing to do with, sorry, not I, with ball 1, doesn't affect what happens with ball 2 and so on. So by the definition of independence, this means that this probability is just a product of the probabilities. Times all of these probabilities.
Could you explain it again? Why is like this 2 equal?
That's the definition of independence. So remember, what's the definition of independence?
I mean, I know, but how do we know that the intersection of the ball 1 not in bin 1 times ball 2 not in bin 2, all those time together is the intersection of it?
That's the assumption that they're independent.
Oh, I see.
So that's part of, you're asking a good question. That's part of the modeling of the problem, right? Like we do this in real life, and who knows what happens in real life, right? Like maybe what I do for ball 1 does affect what I do for ball 2, right? But in the mathematical abstraction of the problem, I'm saying, let's assume we're throwing the balls in a way so that the probability, the distribution, the probability of any event involving ball I, or sorry, ball, I guess I've already used I, ball J doesn't depend on any of the other ones. So then you would get this, right? Or by the chain rule, you'd get a bunch of conditional probabilities, but then you'd be able to just ignore the conditional part because they're independent. Is that okay?
Yeah, got it.
Yeah. So notice how much progress we made. We started off with this very like kind of global question about n balls into n bins. And by using linearity of expectation, so here we use linearity, we've narrowed it down to one ball in one bin. So now I'm throwing ball one into one of these bins randomly. What's the probability it doesn't land in bin number I?
N minus 1.
9/10 to the 10.
Well, someone said n minus 1 over n, and I think that's the right answer, because this is a question about one ball, right? It's equally likely to go into all of these. Each of them, it goes with probability 1 over n. So it doesn't go, it has 1 over n probability of going into this one. So the probability of not going there is 1 minus 1 over n. So the answer you get is 1 minus 1 over n times 1 minus 1 over n. 1 minus 1 over n times. This is 1 minus 1 over n to the n. Which, as you might know from calculus, is very close to 1 over e for large n. Good. So now I've calculated the expectation of one of these. So what's the total number of empty bins? Well, this is the same for every I, right? So it's just n times this, which is about n over e. So which is about I think 37%. So this is a general fact about life, actually. If you have, I mean, many situations can be modeled this way. If you throw 100 balls into 100 bins, about 37% of them will be empty. And it doesn't matter. If you throw 1 million balls in 1 million bins, about 37% of them will be empty. So the interesting thing we've discovered is the number that are empty is just a percentage. It's not, it doesn't depend on n actually, which is highly not obvious. This is, of course, just on average. So any questions about this?
Yeah. So if we just have a single bucket, like, okay, so just looking at a single one of these buckets, if there's a 9/10 chance that you're not going to make it into that bucket, right? Because it's probably going to get into one of the other ones.
You're saying for n equals 10, right?
Yeah, for n equals 10, right? Exactly. So wouldn't it be 9/10 to the 10? And that's the probability of it not.
Absolutely. And that's what this is, right? So in the case n equals 10, then this number here, what is this? Well, it's 9/10 to the 10.
I guess I'm a little bit confused about how we can approximate that to be 1 over, for large n.
For large n, yeah.
Oh.
So by the way, 9/10 to the 10 is not that far from 1 over e, actually, if you actually calculate it. But yeah, for large and you're right, we haven't said what large is. But yeah, I mean, I'm kind of appealing to some stuff maybe you learned in calculus here. But definitely for 100 or 1 million, this number is very close to 1 over e.
I have a question.
Yeah.
So in this question, we use linearity, and like in what kind of case we use like this kind of approach, and in what case we use like the random variable one?
Oh, well, we did use the random variable here, right?
Yeah, but like I mean the approach that like q to the k and 1 minus q n to the k, is that like only 2 different possibility for a certain event? We use that.
You're talking about the Bernoulli trials, like the many coin flips, right?
Yeah, so
Yeah.
in what
So
case?
in that case, I mean, we use linearity to calculate the mean in that case too, right? Remember, it was much easier to use linearity, actually. We calculated the average number of heads in 2 different ways. And the easiest way was to use linearity of expectation. So whenever you see a sum of random variables, think about using linearity.
But for like that kind of question, because a coin only has like tail and head, so there's only like 2 possible like events gonna happen. But in this case, it have like n bins, so
Well, well, I agree, but what was the creative part of this? The creative part was that to imagine that I should define these indicator random variables, right? And these actually only have 2 values, 1 and 0.
but you cannot get the probability for each, like for
No,
1 and 0.
That's a very good point. I did not calculate the probability of there being this many empty bins. I calculated the average number of empty bins. So this is a very good point. I did not calculate the probability of any event here. I calculated an average of some random variable. And those 2 things are not the same.
Yeah, like is there any way that we can find the probability of 1 and 0 in this case?
I see. So your question is, what is the probability of what's 1?
Yeah, so
You
that
mean?
size empty. So it's basically a certain bin is empty.
Oh yeah. Sorry. So we did do that, right? We kind of did that. Like this expectation, E of EXI, according to what we did earlier, this is the probability that bin I is empty.
So it's 1 minus 1 over n.
Yeah.
Then 0 must be 1 minus 1 plus 1 over n. So it's 1 over n.
Oh, you mean the probability that no bin is empty?
Yeah.
Well, okay. No, so this is not helpful for calculating the probability that no bin is empty because these events are not independent, right? The probability that bin 1 is empty is not independent of the probability that bin 2 is empty.
They're not independent.
No, they're not. You can't just multiply them. I mean, also intuitively, they're not, right? If I know that bin 1 has a ball, that gives 1 fewer ball for the rest of the bins. So these events are not independent.
If you want to calculate the probability of having every bin filled, it would just be n permutation because it would be like counting bijective functions.
Exactly, yeah. So you're raising a very good point, which is there's a sample space here, and the size of that is n to the n. And in here, there's some event E where no bin is empty. And that's just a set of permutations, right? If no bin is empty, then every ball went to 1 bin. So it's just an arrangement of the balls in order. So this is n factorial over n to the n, which is actually a very small number. So you can solve this question, but you can't solve it by multiplying these probabilities that bin I is empty because those events aren't independent. So that's an example of, I mean, that's kind of part of the art of probability that you have to find just the right way to break up the events and random variables to make the calculations easy. Does that help?
So are you saying that there is no way to do this problem, or it will be very difficult if we set the random variables to how many bins are empty?
Yeah, okay, well, let's try it. So let's define some other random variable. Let y be the number of, well, no, I mean, we kind of did do that, right? We did look at the number of empty bins, but maybe you're asking, what if I want to calculate the probabilities of the number of bins being empty equal to k, right? what is the probability that X is equal to K? That's what you're asking, right?
Yeah.
I mean, okay, it's not that hard, but it's a little bit, I mean, it's a little bit more annoying. Okay, let's see, right? Well, okay, we can do it by counting. This is the number of ways to put n balls in K bins divided by the total number of ways to put n balls in n bins. Well, that's not that bad. That's K to the n divided by n to the n. Oh, sorry. Times, oh yeah, I don't know. This is actually annoying because, yeah, this is not correct. So by the way, why is this not correct? Anybody see why this is not correct?
Would it be because the balls aren't distinct? Because there would be like the same thing, and so we'd be overcounting by doing this?
No, the balls are distinct.
You will have leftover ones.
Well, the point is that K bins is, we don't know which K bins, right? So okay, maybe you put an n choose K over here. So you choose which K bins. Right? But this is still not good because really this is the number of ways to put n balls in K bins in K bins such that each bin has at least one ball, right? Like, this is not correct because this includes cases where we put where we put all the balls in one bin, for example. Now you can solve this, but it's, as you can see, it's considerably harder than just using linearity of expectations. So I'll just do ... and it's harder. I mean, this is basically not an answer, right? This is. I'm not saying this is a correct approach. I'm just saying if you try to do it this way, it becomes a lot harder. Whereas, because you have to consider how the bins interact, right? Whereas here, you don't have to do that. That's the beauty. You turn this into a problem of one ball and one bin. Does that answer the question?
Yeah.
Okay. Okay. So I'm just going to put this because I haven't verified that this is correct. I don't want people who read the notes to think that this is the right answer, but okay. Okay, so that's one more example of linearity of expectation. So now I want to define the distribution of a random variable and give 3 examples of distributions that are important and come up a lot. So here's the definition. Given a probability space and a random variable, x, which is a function from the probability space to R, the distribution of x is the set of pairs of values of x along with the probability that x takes that value. So, I mean, this is a maybe slightly complicated looking thing, but when I show you examples, you'll see that it's something we've actually been looking at all along. So let me draw a cartoon of it first. The cartoon is related to this picture over here. So as I said, every random variable partitions the sample space into sets, right? Depending on the value that it takes on those outcomes. So all this is saying is, I can make a graph out of this, right? So what can I do? I can plot the range on the x-axis, and then I can plot on the y-axis the probability that x equals r. So, for example, this green set over here, this has some probability. It's an event, right? So I can make a green bar here for that probability. And then this other set here, x equals 2, this has some probability, so I can make some other bar here for that probability. And so that's called the probability distribution. It's not a complicated concept. Oh, whoops, I messed up the indexes here. So this is x equals 3. Oh, whoops. Okay. So x equals 3, and then x equals 2 was here. Looked like it was maybe a little bit bigger than x equals 1. Anyway, yeah, etc. Okay, so let's look at a few examples of distributions of random variables. The simplest example is the Bernoulli distribution. And here, the sample space is the sample space is just you flip a coin, heads or tails, but now you have a bias. The probability of heads is some q, which is a number between, well, could be equal to 0 or 1. This is the bias. And then, okay, sorry, I should use a little p because this is not a subset. This is a point in the sample space. And so the random variable, this is kind of a trivial example. The random variable is just 0 or 1. Or, yeah, there's not even a need to give it a different name, but sure, let's just say it's 1. If S is heads, and 0 if S is tails. So this is kind of a boring example. The probability space just has 2 elements, and they just get mapped to, you almost don't need the notion of a random variable here. Heads gets mapped to, 1. And tails gets mapped to 0. So then
the p that you wrote here means probability, right?
Yeah, this is the probability function, though. It assigns a probability to each outcome. And so the distribution is just well, 0 with probability 1 minus q, and 1 with probability q. And this is just a fancy notation for drawing this graph, right? That you're either 0 or 1. And okay, you're 0 with probability 1 minus q, and 1 with probability q, whatever those are. Okay, that's not that interesting. Let's look at a more interesting example, which we already did. The experiment is flip n coins with bias q. The random variable x is the total number of heads. We already did this last time. And the probability that this number of heads is equal to k, we calculated last time. It's n choose k, q to the k, 1 minus q to the n minus k. And so, and this is the distribution.
This is in some ways a binomial distribution.
Yeah, so this is called the binomial distribution. So k goes from 0 to n. This is called the binomial distribution because it's related to the binomial theorem. as we saw last time. That's why the numbers add up to 1. And let me just draw a picture of this distribution. So last time we calculated the expectation of this random variable was just n times q. And here's a cartoon of what the distribution function of this random variable looks like. So on the x-axis here, you have the number 0, 1, 2, ... k up to n. And and up here you have the probability that the random variable is equal to r. So this is this is k. This is the probability that the random variable is equal to k. And if you draw this, it looks something like, I mean, it's not really a curve. It's just a discrete set of points. And it turns out it reaches its maximum at, well, as I said, it's not a curve. It reaches its maximum around NQ. And if you adjust the, it's actually a family of distributions, right? Because there's this bias parameter Q. If you now, if you shrink Q, then this is going to look very different, right? So if you have small q, it's going to look something like, I mean, that's not a very good cartoon. So this is what happens with small q. There's low probability of being heads. And for large q, you will move this, it'll sort of shift to the right. That's what it looks like. So the distribution of x is this function that gives the probabilities of all the outcomes. That's the distribution. Any questions about this? Okay, so let's do one more example which comes up a lot. This is the geometric distribution. And the question I want to ask here is, so what's the experiment? The experiment is I flip a coin of bias Q repeatedly until I see heads. So repeatedly means two things. It means that the flips are independent. Okay, but the main difference in the geometric distribution, binomial distribution, is this until. In the binomial distribution, I flip n coins, right? I flip a coin n times. That's fixed in advance, right? The parameter n is used to define the binomial distribution. In the geometric distribution, I do it until I see a head. It could be forever. It could be like, there's no bound on how many times I flip the coin. So what's the sample space here? Sample space is all outcomes. So what do outcomes of this experiment look like? How would you describe a particular outcome of this experiment?
Heads or tails?
Okay, so if I get heads, then indeed the experiment is over. But if I get tails, that's not really an outcome, right? Because I'm not flipping a fixed number of times. I'm doing it until I see heads. So tails is actually not an outcome of this experiment.
How many flips until you get heads?
How many flips until you get heads? Yeah, that's a good way to put it. But I can say a little bit more about the flips. What do the flips look like until I get a head?
All tails.
Number of tails in a row.
All tails.
Yeah, tails. So there's heads, tails, heads, tails, tails, heads, et cetera, et cetera, et cetera. And the general thing is some m number of tails followed by heads. And this goes on forever. So this is an infinite sample space. Our first example of an infinite sample space, but it's okay. Everything still works. It's a set. What's the probability function on this sample space? What's the probability of seeing m tails followed by one head? So now we have to think about the individual flips, right? For each coin flip, I have a 1 minus q chance of getting. So this bias q means the probability of heads. Or yeah, let me just write little p to be consistent. It's q. So the probability of tails is 1 minus q. So what's the probability of? I mean, okay, let's just do it. What's the probability of getting a heads just on the first flip?
1/2.
Or Q.
Q. So it's 1/2 in general, but I'm sorry, 1/2 if it's unbiased, but this is biased, so it's Q. What's the probability of getting tails and then heads? Well, they're independent coin flips. So what's the probability of first getting tails, then getting heads?
1 minus Q times Q.
1 minus Q times Q. And then you keep repeating this. So in general, the probability of getting M tails followed by heads is 1 minus Q to the M times Q. And I use independence. Whether or not the next coin is heads doesn't depend on what I did in the past. That's why I get to multiply the probabilities. Any questions about this calculation? Okay, so I want to do a sanity check. So why do these numbers add up to 1? So this can go from m equals 0 to infinity. I have to add up these probabilities. Why are these equal to 1? Well, let's calculate it. So this is an infinite series. So I get q times 1 minus q to the m. And now if you remember your calculus, I mean, I can pull this q out in front. Does anybody recognize the series?
Would it be just a geometric series with ratio 1 minus q?
Yeah, it's a geometric series. So this requires some knowledge of, I suppose, let's call it calculus, but this is a geometric series, which is why this is called the geometric distribution. And that's just one. So good, this is a legitimate probability distribution. So this leads us to actually an interesting kind of conceptual conclusion, which is what's the probability of eventually seeing a heads?
One.
Okay, so this takes a little while to wrap your head around, but what they're saying is, I mean, okay, unless Q is 0. If Q is 0, this doesn't work, right? You get 0 divided by 0. So let's assume Q is positive. If Q is 0, then you never see a heads, and this doesn't make sense, right? Then there's no experiment. But if Q is positive, what this is saying is you will surely eventually see a heads if you do this experiment. And I mean, this is basically this is actually just, it's the same principle as this business of if you have monkeys on a typewriter, if you let them run forever, they will type, the works of Shakespeare or something like that. Okay. So now, what's the expected value of this random variable? So let's define a random variable. Let x x is the number of trials until first success. So x is so I don't want to be off by 1 here. Yeah, okay, so X is the number of flips. I forget if it's before the first head or when you up including the first head. Let me just make sure I get this right. Yeah, okay. This is the yeah. So this is the number of flips until the first head. So that means X of T to the MH is M plus 1. Because I have one more flip after all the tails, right? Now, what's the expected value? So this is asking how long do I have to wait before I succeed on average? So what's the expectation of X? Well, let's use the definition of expectation. In this case, it doesn't matter which one we use because each point in the sample space corresponds to one point in the range. So what you end up getting is that this is Q times 1 plus 2 times Q times 1 minus Q plus 3 times Q times 1 minus Q squared. And so in general, you get this sum. You get summation M plus 1 Q times 1 minus Q to the M.
I mean, the coefficient like means that the number of random variables is that like what we use in this Bernoulli trial.
Yeah, so this coefficient is a value of the random variable, right? So this is the probability that X equals M plus 1. And this is, the value of the random variable, right?
Oh, and because like each like possibility only have one term, so there's actually a 1 times that before, but we just didn't write it. Is that
no, there's no 1 times. So you never do counting here, right? You just have the value of the random variable times the probability of that appearing. But yeah, you're saying that this is just equal to the probability of one outcome, and that's correct. But really, we're checking the probability of this event.
I mean, last time when we're doing like those biased coins, it's like we use the terms of terms times like this.
Yeah, you're right. So in this case, the sample space is different.
Yeah, so it's just like each term have one event in it.
Yeah, you're right. That's right. Okay. So now calculating this is a little bit outside the scope of the course. It requires calculus. If you've done calculus, you can do it. Let's calculate this using calculus. So I'm going to do is I'm going to recall from above, actually, that the sum of this 1 minus Q to the M, Q times 1 minus Q to the M, this is 1, right? From above. So what I'm going to do is I'm going to move this Q to the other side. I can do that. Oh, no, sorry. What am I doing? I missed the m+1. That's the most important part. Wait, so let's see, how do I want to do this?
Can we do like a derivative method? Like we consider the sum as m goes from 0 to infinity of like 1 minus q to the m. Figure out what that is, then take its derivative with respect to that doesn't quite work. I guess you could take it with respect to 1 minus q actually. So
Yeah,
that would work.
That will work. So what I'm trying to do is figure out how to best present that.
Okay.
So I want to make sure I don't mess up this m versus m+1 thing. Okay, so before we do anything, let's notice that if you take the derivative of the series with respect to q, so this is why it's a little bit outside the scope of this course, because I don't actually know if everyone has taken this or looked at the or actually, yeah, let's move this q to the other side. That's fine. So if you take the derivative of this, then this is the part which you have to justify using calculus, which I'm not going to do in this course, that you can push the derivative inside the sum. That actually requires a proof. And this is now summation. M goes from 0 to infinity. You get m times 1 minus q to the m minus 1 times minus 1 because I took the derivative. So this looks quite a bit like what's written up over there. Except it looks like some of the indices are kind of off by 1. Okay. Can never figure out off by 1 errors on the fly. Let me see. Well, okay, so okay, let me do it this way. So if you look at 1 over 1 minus q, maybe 1 minus q. Then this is equal to, yeah, okay, this is better. Let's look at this function. This is equal to this. Now, if we differentiate both sides with respect to q and push this inside the derivative, then you get and you get a minus 1 over here. And if you do this, this is just 1 over q, so you just get minus 1 over q squared. And now if you rearrange this, so if you write this down, so there's an m equals 0 term here, which doesn't actually count because it's multiplied by 0. right? Because so if you cancel the negative signs from both sides, then you get that 1 over q squared equals the summation m goes from 1 to infinity of m times 1 minus q to the m minus 1. And now if you move this q over to the other side, you get this. But this is actually the same as what's written over in the box. I just replaced m by m plus 1 and started at 1 instead of 0. Right? If you take this and you just change the variable m plus 1, you rename it to be m, you get exactly this formula. Okay, so I kind of pedagogically did this the wrong way here. The right thing to do is to look at this formula, differentiate both sides, and now you get this identity. And so then the conclusion is that the expectation of this random variable is 1 over q. So this, I agree, this is a little bit magical. And well, in some sense, it's a trick. There's a somewhat more sophisticated way to do it, but that needs some more concepts. That's a little easier. But anyway, this is a proof that the expectation is 1 over q. This is a question about infinite series that we solved using calculus. So the geometric distribution has the average number of times you need to flip a coin of bias q until you see a head is 1 over q. And this number goes up as q gets smaller, which makes sense, right? If your chance of succeeding is getting smaller, you have to wait longer. And the beauty of this is that you have to wait exactly just 1 over what the bias is. So this is something that, if you wanted to answer this question of how long do monkeys need to type before getting a work of Shakespeare, well, you need to calculate the probability of getting a work of Shakespeare, which I think is probably less than the number of atoms in the universe or something like that. And they need to wait 1 over, they need to wait that long. They need to wait that 1 over that, which is the number of atoms in the universe. So it's not really ever going to happen. And let me just draw a picture of the geometric distribution. Well, the probability that this random variable is equal to m is what I said earlier. So this is the distribution. And the picture is it's a different shape from okay, so it's not a good picture. Okay, if you want to see a picture, let's just go look at Wikipedia. Yeah, so if you go to Wikipedia, you can see pictures of what these distributions look like. And this comes up a lot in, for example, it comes up in the question of how long, suppose at every, in every time interval, some system has a probability of failing. And you want to know how long is it before it's actually going to fail? Well, the answer is if the failure, if you believe that you have independent trials again and again and again until you fail, then the answer is 1 over the probability of failure in any one trial. Okay. So those are 3 probability distributions. I'll just do algebra of random variables next time, since I end up spending a lot of time on these examples. But these are 3 of the most common examples that come up in applications. So any comments or questions on these examples? Okay, so I'm just going to spend the last 10 minutes doing a very quick review. So we basically did 3 things since the previous midterm. So the first is chapter 5, which is induction. And what are the ingredients in a proof by induction? Well, the first one and the most important one to get right is the inductive hypothesis, which is a propositional function where n is a positive integer. So this is the inductive hypothesis. And then it's this, that's the first ingredient. The second ingredient is a proof of the basis step. And the third ingredient is a proof of the inductive hypothesis. Of the inductive step, sorry. And then if you do all these things, the conclusion is you get the statement for all integers. So this is the inductive step. And then there's a version of this which is strong induction, which is not really a fundamentally different thing. That's just what we call it if you use P1 through Pk, or if you show that P1 through Pk imply Pk plus 1. Now, what are the key ideas in this part of the course? I mean, I'd say the main idea in induction is you want to prove a statement. Often you want to prove a statement about objects of size n. So that might be like a tiling of a board, or it might be a factorization of numbers with up to n factors, or it might just be the number n. And the general idea is you want to reduce a problem to a smaller problem of the same type. And this is, in setting up the induction, this is the key thing you want to find. You want to find an inductive hypothesis that nicely relates whatever your statement is of size n, size n to things that are smaller. So for example, if you remember the example of this, this tiling a board by triominoes. We related what happens on the big board to smaller ones. A counterintuitive feature, there are two counterintuitive features of induction. So one is it's often easier to prove an infinite family of statements than to prove just one of them. Than just like, let's say P of 1,000. Often it's easier. So this logically, it sounds weird, right? I'm asking you to do more work. I'm asking you to prove something stronger, but often it's easier because you get to, you start kind of proving it slowly. You're proving small cases first, then slightly bigger cases, then bigger ones, and so on. And then finally, which is related to item 2, you have to choose just the right inductive hypothesis. Sometimes it's easier if the inductive hypothesis is stronger. And I would say the real creativity, comes in 2 places. One is in choosing the inductive hypothesis. This is very important. And the second, of course, is in these proofs, which could be arbitrarily complicated. But if you don't get the inductive hypothesis right, the proofs might not work. And when that happens, revisit your inductive hypothesis. And then keep trying to prove it, but it's really important to get the inductive hypothesis right. Okay, then the next chapter we did was induction. Was counting. Or actually chapter 6 and 8. We did basic counting and advanced counting. And I would say the key principle of counting is that to count a collection of objects, you define a sequence of choices. That's the single most important principle of counting. So to count a collection of objects, define a process, by which I mean a sequence of choices, which uniquely construct objects from a collection. So really the picture is you're implicitly setting up a bijection between ways of making choices to the set of objects. And the point is that these choices you can break into smaller sub-choices. And that's where the creativity comes in. How do you choose this so that you can get these smaller choices? And then ideally, these are easy, whereas the original object might have been hard. That is the real underlying principle of counting. Now, many people have asked me this about counting, so remark, which is how do you do, so the key is that this is a bijection, right? And people have asked me that how formally do you need to prove that this thing is a bijection, right? Now, in this course, it's usually not that hard to prove that these things are one-to-one and onto once you have precisely specified it. It's usually that's not the hard part. The hard part is coming up with it and precisely specifying it. So it's enough to precisely specify the correspondence. Between choices and objects. You don't have to formally prove that it's one-to-one or onto. Okay, so sometimes it's helpful to say, helpful to explain why. It's helpful to explain, which part of the object comes from which choice, which features of the object correspond to which choices. So the more detail you specify about what this correspondence is, that makes it easier to see that it's a bijection. And I would say that's kind of how the proofs in the book are written and how proofs in the class were written also. That's a good general principle. Now, okay, in addition to this key principle, there are a few rules. There's the sum rule, the product rule, and the division rule. Plus, there's this, you can use tree diagrams to organize these rules in a way so that you don't get confused. And then there are a few basic counts which keep coming up. These are counting the number of subsets, counting the number of permutations, putting indistinguishable balls into distinguishable bins, or putting distinguishable balls into distinguishable bins. These are the 4 basic counts. And I would say the creativity is in knowing how to use these rules to reduce your complicated counting problem to these basic counts. I mean, yeah. So there aren't that many tools that are used here, but the interesting part is how to combine them. And then we had the notion of a combinatorial proof, which is just in a sentence, it's just to, you just, if you count the same thing in two different ways, you can prove that two different formulas are equal. And then, okay, then there are two advanced counting techniques, which are inclusion, exclusion. And then the second one was expressing the outcome of a counting problem as a recurrence relation. And one connection I want to emphasize is you may want to revisit this in the context of recursive definitions in chapter 5. Okay. So any questions? So precisely is very important here. So there is the logical structure is not that complicated, but it's very important to precisely specify these processes that you're using to count objects in the counting section. Okay, so I guess I'm out of time. What do I want to quickly say about probability theory? Well, I almost included a survey in the last lecture, actually, right? So see lecture 19 for a single slide with a list of all the tools you need up to lecture 18. The basic idea, as I said, is how do you calculate the probabilities of some events given the probabilities of other events? And again, the interesting part is how do you break down complicated events into simpler ones using the rules of probability? So anyway, just see lecture 19. I won't say more about that, but yeah, I don't know. I hope that was helpful. But yeah, good luck on the midterm.
Sir, have you posted the solutions to the
yes, sorry. I'm going to post the solutions just now after this lecture.
Okay.
Thank you.
Yep, thank you.
You.
Thanks.
Thank you.